Hello. In this video, we are going to see the transient stability. We had already seen the steady state stability of power system analysis. The transient stability, in transient stability, we will be able to determine whether the system is in synchronism or not after the machine had subjected to a several disturbance or large disturbance. As I said, for steady state stability, we will be seeing small disturbance. For transient stability, we will be seeing large disturbance. The large disturbance may be due to sudden application of load, that is increasing. Suddenly the load may be increased, or loss of generation, loss of large load, or fault on the system. In most of the disturbances, the oscillations will be having a magnitude such that the linearization is not possible. So we need to solve the nonlinear swing equation to do the transient stability analysis. To solve the swing equation, we had three methods. For transient stability analysis, for solving the swing equation, we had three methods. They are equal area criteria method, modified Euler method, Runge-Kutta method. Now, in this video, we will see what is meant by equal area criteria method. A method known as equal area criterion can be used for quick prediction of the stability. This method is generally based on a graphical interpretation of energy stored in the machine. Now, this method is applicable to one machine system connected to infinite bus bar or two machine system. Why? Because it provides physical insight to the dynamic behavior of the machine. Application of this method to analyze a single machine connected to large system. Now let us see that. Now let us consider a synchronous machine connected to an infinite bus bar. Now we know that the swing equation is, this is the swing equation. We know this is the swing equation. Now, as I had already said, PM by SB and PE by SB can be written as per unit values. Why? Because per unit is actual by base. So I am writing this PM by SB as PM per unit and PE by SB as PE per unit and sending this to the other side. I am sending this here so that I will get this term by F naught by H. Now I am multiplying 2 d del by dt on both sides. So what I will get? 2 d del by dt into d square del by dt square is equal to pi F naught by H into PM per unit minus PE per unit into 2 into d del by dt, d del by dt. Now, this whole term, how can we write this whole term as? See here, d by dt of, normally in generally, d by dt of t square. What is the d by dt of t square? 2t into dt by dt, dt gets cancelled, that is 2t. So d by dt of t square is 2t. Similarly, you think you assume this total as a variable, then what you will get? D by dt of d del by dt square is equal to 2 into d del by dt into d by dt of d del by dt. This total term is one thing. You don't get confused. As it is, d by dx of x square is 2x dx by dx. D by dt of d del by dt whole square is equals to 2 into d del by dt into d by dt of d del by dt. Now, if you see here, 2 into d del by dt into, here also there is dt, here also there is dt, and d square del by dt square. So now what we had this term here. See here, 2 into d del by dt into d square del by dt square. So this can be written as d by dt of d del by dt whole square is equals to pi F naught by H, PM per unit minus PE per unit into 2 into d del by dt. This dt gets cancelled. Now, what we had? D del by dt is equal to, from this, I am extracting this term alone. So what I will get? This d, if we send this d to the other side, it will become as an integral. So, and this is a constant. Why? Because there is no time component in this. So this is a constant. So I took outside. And this 2 is also constant. So this 2 also I am writing outside. 2 pi F naught by H. This d, when I send this side, it will become integral PM minus PU Pm minus Pe. Now, this integral limits are I am taking from del naught to del. So, 2 pi f naught by h integral del naught to del Pm minus Pe d del. Now, this is what d del by dt whole square. If I want d del by dt, I can take square root of 2 pi f naught by h integral del naught to del Pm per unit minus Pe per unit d del. Now, according to equal area criteria, from this equation, for stability, what we should do, this Pm per unit for stability, this total integral term should be equal to 0. That is, this equation, actually this complete equation, gives the relative speed of the machine with respect to synchronously revolving reference frame. Now, for stability, the speed must become 0 at some time after the disturbance. So what we will do, we will equate this integral to 0. When we equate this integral del naught to del Pm per unit minus Pe per unit detail is equal to 0. If we observe that graphically, we know that this is the load curve. That is curve with a Pe with respect to del. Now here what we had, this is the curve and this is the P max. Now we are considering the machine operating at the equilibrium point del naught. So let the equilibrium point be this. This is del naught. Now, corresponding to that mechanical input, power input is Pm naught. When the machine is operating at del naught, corresponding mechanical power, actually here y-axis is Pe and x-axis is del. When we are taking x-axis del naught, corresponding y-axis component is Pm naught. That is, Pe at this point, Pe is equals to Pm naught here. Then, now we will suddenly consider a step increase in the input power. Now we are increasing a step increase in the input power by horizontal line Pm1. Since Pm1 is greater than Pe naught, the acceleration power on the rotor is positive and the power angle del increases. See here, as this is Pm1 is above Pm naught, del also increases. Corresponding del also will be more. The excess energy stored in the rotor during the initial acceleration, now we are seeing. See, actually, we are equating this area, the area in this, with the area in this curve. That is the equal area criteria. How to equate this area? What is this area? This is actually between the x limits del naught to del upper line. This line, actually, what is this line? This line is Pm1. And this curve is P, that is load curve. So, integral under the limits, integral del naught to del Pm minus Pe gives the area. Actually, integration will give area, we know that. So, to get this area, the small element area, what we are doing, integral del naught to del 1, Pm1 minus Pe we are doing. That is this term. This term represents this area. This area. Now, as I said, for the stability, we should equate this with this. What is this area actually? Here, if you see which is upside we had Pe. Upper side we are having Pe. And lower side what we had, this is actually Pm1. And this point is del max. So under the limits del 1 to del max, from del 1 to del max, Pe minus Pm1 d del will give you this area. This area is given by integral del 1 to del max Pe minus Pm1. That will give this area. That is this term. By using equal area criteria, we are equating these two terms for getting the stability condition. Now let us see. See here, I am splitting this PM1 minus PE into d del. I am splitting the integral for the two terms. Integral del naught to del 1 PM1 d del minus integral del naught to del 1 PE d del, which is equal to integral del 1 to del max. What is this PE? PE is load curve. We know we already derived this PE equation for the load equation or power angle equation, power angle curve. This is power angle curve, right? Relation, the curve between power and load angle del. So PE is equals to P max into sin del. We had already derived this in the steady state stability. So now I am using this. See, this PE and here we had a term PE. This both PEs can be represented as P max into sin del. Integral del naught to del 1 PM1 d del minus integral del naught to del 1 PE d del is equals to integral del 1 to del max PE d del. That is PE is actually P max sin del minus integral del 1 to del max PM1 d del. Now, since this PM1 is constant, what we will get PM1 into del PM1 into del with the del having a limits of del naught to del 1. So PM1 into, if you apply the limits, what we'll get PM1 into del 1 minus del naught minus, I am replacing this PE with P max sin del. That is del naught to del 1 P max sin del d del is equals to del 1 to del max. I am rewriting this term as it is minus PM1 d del. PM1 d del. This PM1 is again constant. So the same thing, this can be written as here actually it is PM1. PM1 into del. We will get the integral of d del is del with the limits del 1 to del max. If we substitute the limits, upper limit minus lower limit will give you del max minus del 1. Now, I am multiplying it. PM1 del 1. This is PM1 del 1. PM1 del 1 minus PM1 del naught here. Here it is downside. Plus P max is constant and the integration of sin del is minus cos del. So this minus and here integral of sin del is minus cos del, that minus compensated. So we'll get plus P max cos del 1. Actually cos del, what we will get? Minus cos del. Integral of sin del is minus cos del. And again the minus cos del will be having a limits of del naught to del 1. This is the integration of sin del when we integrate this term. So this minus and that minus, if we multiply, you will get plus P max cos del 1 minus P max cos del naught, this total term is equal to, here what we had, here also we had sin del with a limits del 1 to del max, but here in front there is no minus, so we'll get minus P max cos del max upper limit and minus of minus plus P max cos del 1 minus PM1 del max plus PM1 del 1. Now if you observe both sides, here we had PM1 del 1 and here we had PM1 del 1 which gets cancelled, and here we had P max cos del 1 and here you have P max cos del 1 which we can get cancelled. So now what we will have, what are the terms left over? Here we had minus PM1 del max. I am taking this term to that side. What I will get? PM1 del max minus PM1 del naught. I am taking PM1 common. PM1 del max minus del naught is equal to, and I am taking this term to the other side. This term I am taking to other side. this minus P max cos del naught I am taking to other side here. What I will get here plus cos del naught minus P max cos del max. This is the terms which are left. So we got this equation. Now from this what we can write? What we had PM1 del max minus del naught is equals to P max cos del naught minus cos del max, cos del naught minus cos del max. Now we know that PM is equals to P max sin del max. So what I am writing, this PM1 I am replacing as P max sin del max. Why? Because when PE, normally we will tell PE is equals to PM1. So what is PE is equals to PM1? When PE is equals to PM1 from this curve, this is PM1. At this point, PE is equals to PM1. So at this point, if we consider PE at this point is, what is at this point? PE can be written as PM sin del max. At that point, del is actually del max. So PM sin del max. So what will happen? This PM1 I am replacing as P max sin del max into del max minus del naught, which is equals to P max into cos del naught minus cos del max. This P max gets cancelled. And what we will get? Del max minus del naught into sin del max. This minus cos del max, I am bringing this to other side here. So what I will get plus cos del max is equals to cos del naught. Now in this, if you observe, what we got? This is the equation what we had got till now. Now, if you see, let us move on into the application. Now, this equation is nonlinear algebraic equation, which can be solved by the iterative techniques for del max. Once del max is obtained, the maximum permissible power or the transient stability limit is found. When you solve it, what we'll get now? Generally, PM is equals to P max sin del 1, where del 1 is equals to pi minus del max. This is the general derivation. Now let us go on to application specific. We had two applications. This is the first application where we had a fault here. This is at this point we had a fault. And the second application, we will be having a fault at this middle point. Now here what will happen? If you see here, the critical clearing angle is reached when any further increase in del 1 causes the area A2. Here, if you see, this is the area A2 and this is the area A1. Let us assume this is area A2 and this is area A1. Now, the critical clearing angle is reached when there is any further increase in del 1. This is the critical, this is the, if you increase this, this line, when the further increase in del 1 causes the area A2 representing decelerating energy to become less than the area representing the accelerating. Okay, what I mean is, if this is the actually, if you see here, it is accelerating. Before reaching this maximum value, it is accelerating. That is, as P increases, this is accelerating. Why? Because as P increases, del is increasing. So here it is accelerating. After the P max is reached, it is decelerating. Here it is decelerating region. Now, if you see, this is the critical line which is separating the accelerating region and decelerating region. If you increase this del 1, if there is any increase in the del 1, what will happen? A2 will, if del 1 is increased, A2 will be more than A1. That is, decelerating area will be more than the accelerating area. So the stability will be, the system will become unstable. So what we will tell, the boundary condition at which the system is stable, the boundary condition, the critical clearing angle is the angle for which the system remains in the stability. If we increase or decrease any further, the system will go to unstable. So this is said to be the critical clearing angle del C. Now in this, these two areas should be equal. So what is this area? Here it is PM. So, and here it is 0, no? It is, this area is ending at 0. So what we can write? From del naught to del 1, integral del naught to del 1, PM minus 0 into d del. That is this one, this term. And then here we had this curve upper PE, and the lower part of the curve is actually PM. So, and the limits are del 1 and del max. So, to equate the area for these two things, this area can be represented as integral del naught to del 1 PM minus 0 d del, and this area can be represented as limits are del 1 to del max. So, integral del 1 to del max PE minus PM. That is this area. So we are equating these two. This PE, we already know PE is equals to P max into sin del. Now, here if we integrate, what we'll get? PM into del 1 minus del naught, which is equals to integral del 1 to del max, P max sin del d del, minus integral del 1 to del max, PM d del. That's what I had written here. See, PM into del 1 minus del naught is equals to integral del 1 to del max, P max sin del d del, minus integral del 1 to del max, PM d del. This P max sin del is P. Now, I am multiplying PM into del 1 minus PM into del naught is equal to sin del integration is minus cos del. So, minus cos del max and minus of minus plus cos del 1 minus PM into, here it will come only del with the limits del 1 to del max. So, del max minus del 1. If I multiply it, minus PM del max, minus into minus plus PM del 1. This PM del 1 gets cancelled. Now what we have, I am taking this minus PM del max to the other side. I am taking this to the other side. So what I will get, PM into del max minus del naught is equal to P max into cos del 1 minus cos del max. Now as I had said, critical angle is del C. Corresponding time is critical clearing time. Critical clearing angle is del C. Corresponding time is critical clearing time TC. Now let us find out that when del is equals to del C, as I said, del 1, the line del 1 is acting as a boundary thing. If del 1 increases and deceleration area, when this del 1 moves like this, what will happen? There will be the change in the area, decelerating area and the accelerating area will not be equal. There will be a change. So we should be careful. That is the critical clearing angle. So when del is equals to del 1, what will happen? PM into del C minus del naught is equals to P max into cos del C minus cos del max minus PM into del max minus del C. How we got this equation? Substitute this del 1 is equals to del C. Then you will get this equation where we should substitute here. You substitute in this equation. Let me take this equation. Let me take yeah. Let me take this equation as 1. Now I am substituting del 1 is equals to in del C in equation number 1. What I will get? The same thing. That is this Pm into del C minus del naught is equals to same thing. In the next step you can see here. See Pm del C minus Pm del naught is equals to let me minimize it. Now you can see. Pm del C. Here I am placing del C. Pm del C minus Pm del naught is equals to Pmax cos del C. Pmax cos del C minus Pmax cos del max minus Pm del max plus Pm del 1. Here del 1, wherever del 1 is there, here we are getting del C. This Pm del C gets cancelled. From this, we are getting the cos del C term. You can directly, instead of substituting there, you can directly substitute in this also. Here, directly you can substitute here. What we will get? Cos del C is equals to, from this, Pm into this minus Pm del max, I am taking to the other side. So what I will get? Pm into del max minus del naught plus this minus Pm cos del max also I am taking to the other side. So I will get here plus P max cos del max, and this P max coefficient comes to denominator. So cos del C. Now we got an equation for cos del C. If you split this P max denominator individually, Pm by P max into del max minus del naught plus cos del max. This is the equation. This is the equation for critical clearing angle. From this, you can find del C. Critical clearing angle. Remember one thing, this critical clearing angle formula is applicable when the fault is at the shown area only. That is, we had taken an application alone. For that application, we are deriving this critical clearing angle. This formula will vary for different applications. This is applicable only when the fault is at this point here. When the fault is here, then you can use the critical clearing angle formula which we had derived now. And let us derive the critical clearing time Tc when the fault is at this point. See, now when at del C, what will happen? PE is equals to 0 in swing equation. So what will happen? This is actually the swing equation. Substitute PE is equals to 0 in the swing equation. What we will get? This term will become 0. So what will come? D square del by dt square is equals to pi f naught by h. This pi f naught by h I am sending here. Pi f naught by h into Pm per unit. I am leaving that per unit. Actually, it is per unit. Instead of writing every time, I am leaving it. Now, from this, I am integrating this d square del by dt square. If I send one differentiation to the other side, it will become an integration. So I am integrating it. What I will get? If I send to the other side, it will be integrated. This dt is becoming t. This dt will become t. Now, from this d del is equals to pi f naught by h Pm t dt. So what will be, again I am integrating. What I will get? Del is equals to integral pi f naught by h Pm t dt. Now this t dt will become t square. And the total, we had two integrations, no. So there will be a constant. I am taking that constant as del naught. See here, actually, how this equation is there, no? This equation can be written as d square del by dt square can be written as d by dt of d del by dt. I can send this dt to the other side. So what I will get? D of d del by dt is equals to pi f naught by h Pm into dt. When I send this differential to the other side, I am getting integral. That is, this is that equation. Similarly, after integrating this dt will become t. Again, I am sending to this dt to the other side. When I send this dt to the other side, what I am getting? This equation I am getting. Now I am sending this d to the other side. I am getting this integral. This d to the other side will become integral. So finally, I got this equation. Now, in this equation, we can find the value of t. This is the critical clearing time. Why? Why it is said to be critical clearing time? Why? Because we had taken PE is equals to 0. When the angle is a critical clearing angle, it will be stable and the area will be equal. So PE is equals to 0. We are taking in the swing equation. So corresponding time is the critical clearing time. I am finding the value of this t from that, which is this equation. This is the formula for critical clearing time. This critical clearing time formula is same for all the applications. Only, but the value will be different. Why the value will be different? Because here we had del C, that is critical clearing angle. Whenever we need to find the critical clearing time, before finding critical clearing time, we should find the critical clearing angle. Why? Because we need to substitute the critical clearing angle in this. So if the critical clearing angle is different, obviously critical clearing time is different. This formula remains same. This is critical clearing time. Critical clearing time. This critical clearing time remains constant for all applications. The same formula you can use for all the both. Actually, we had only 2 applications. So this time, critical clearing time formula for both applications. This validates for both applications. The next application, now we will see that. But here, the critical clearing angle, this is only for application 1. Application 2, we will derive now. As this critical clearing angle is varying for the application, corresponding critical clearing time also vary. Why? Because critical clearing time is, formula is in terms of critical clearing angle. Application 1. That is the, when here we had a thing, generator, and here there is a bus bar, and here we had 2 through transmission lines. We are connecting it to the infinite bus bar. And here we had the fault. Here there is a fault. That is at this point. When the fault is here, that is the application 1. Now let us move on to the next application. Application 2 is the fault is in the middle of the transmission line. Here we had the fault. When we had fault at this point, what we should do? Now let us see what happens if the fault is at middle. Now let us assume this is actually when you find the value of PE in terms of del. Actually, for the transient stability, any problem you are doing, we should find the value of PE, that is P max sin del, before occurring of fault, during occurring of fault, and after occurring of fault. As I said before, see here we got this equation, right? In this equation we got generally. In this equation, we need to find the value of del. We need to find the value of del max. This del max, how we are finding this del max? We are finding by using iterative methods. The iterative methods which we are using to find this del max are step-by-step or point-by-point method, modified Euler method, and Runge-Kutta method. So whenever you are doing a modified Euler method, Runge-Kutta method, or step-by-step method, so you should know what is meant by equal area criteria and why we are using those iterative methods. We are using those iterative methods for finding the solution of this nonlinear algebraic equation, which we had derived in the equal area criteria. So now let us see. Here there is a fault. Now if you draw the graph for the power angle curve before fault condition, after fault condition, and during fault condition, this will be the graph which you are getting. Before will be the highest, and then we will be having after, and then we will be having during. Before, after, and during. I am considering the before peak as P1 max. Normally, first we will find before. So let me take that peak as P1 max, and then we will be finding during, right? So during peak is P2 max, and then we'll be finding after. So after peak is P3 max. Now in this is the mechanical power PM. Now here what should be equal? This area should be equal to this area. How we will equate? Let me take corresponding curve as this is what before. So before na PE1, which is corresponding, PE1 is equals to P1 max sine del 1. And the peak is P1 max. And this is after, second is after. So corresponding after is actually before, during, after. That is the procedure of solving. So before is PE1, which is equals to P max, P1 max sine del 1. Corresponding peak is P1 max. And then this is during curve. During is PE2. We will find, this is the second thing we should find. So this is PE2. PE2 is equals to P2 max sine del 2. So we are taking the curve peak as P2 max. Then the third graph is after, that is PE3, which is equals to P3 max, PE3, which is equals to P3 max sine del 3. So corresponding peak is P3 max. Now what is this area? This is PM and this is PE2. So PM minus PE2, actually during PED I had represented, let us take it as PE2, that is during, is equals to, this is after minus PM. So PEA minus PM. Here PEA na, A is after, that is 3. This PM will be in between after and during. Now PM, I am splitting it, integral del naught to del C PM d del minus integral del naught to del C PE during d del. Integral del naught to del C PM d del is PM into del C minus del naught. And integral del naught to del C PE during del C is PE during is PE2, that is P2 max sine del. So that sine del, if we integrate, we will be getting minus cos del, and this minus and the minus are compensated. So we got plus here. P2 max sine del, difference integration is cos del with upper limit cos del C minus cos del naught. Similarly here, PEA, that is after, that is PE3. PE3 is P3 max sine del 3 or P3 max sine del. When we integrate sine del, we get cos. So minus P3 max cos del max minus cos del C. If you take this minus of minus, it will become plus. Then this minus PM into del max minus del C. This is the integration. As I had said, PED is during, or we can take this is 2. That is P2 max sine del max. PE after is 3. That is P3 max sine del naught. For remembering this graph, when we are able to remember this graph correctly, then we can do the derivation properly. So for remembering this graph, you can think like this. See, del naught to PM before intersection. Where is del naught? This is del naught and PM. This is the point. This del naught and PM before intersection. It is starting point. That is this del naught and PM. Actually, del naught and PM will intersect at 3 points. No, during it will intersect, after it will intersect, and before it will intersect. These 3 points it will intersect. So you should start the line P back. PM should be taken for before. So del naught to PM for before condition wherever it is intersecting. You should not take the area from here. We should take the area from here. So intersection, that is the starting thing. And the ending thing is del max. That is this del max PM after intersection of, this is the after graph. This is the intersection point of del max and PM with the after graph. This is before graph. Del naught PM and this after before graph. This 3 intersection is the starting point. Del max PM and before after graph. See, this graph is after graph. So for remembering the graph, what you can do is, it will start at the intersection point of del naught PM and before graph. This is the before graph. No, this is the before graph. And it will be ending at the intersection of del max PM and after graph. That is, this is the after graph. So in this way you can remember. Okay, now see here, till we had derived till here, right? Now if you multiply this PM with del C, PM into del C minus PM into del naught plus P2 max cos del C minus P2 max cos del naught is equals to minus P3 max cos del max plus P3 max cos del naught, del C plus P3 max cos del C minus PM del max plus PM del C. This PM del C gets cancelled. Now, this is the equation which we had got. What? This is the left. This is the leftover things. This and all are left. After cancelling that. Now here, we need cos del C. Where is cos del C? To find critical clearing angle. In the second application, here we had cos del C and here we had cos del C. So I am taking cos del C terms one side and rearranging. I will get this equation. Cos del C into P2 max minus P3 max is equal to PM into del naught minus del max plus P2 max cos del naught minus P3 max cos del max. From this, I am getting the critical clearing angle for the second application. That is when fault is at the middle of the transmission line. That is at this point. Now you can substitute this cos del C. From this, you can find the value of del C, that is cos inverse. And then you can substitute the value of del C in the TC formula, critical clearing time, to get the critical clearing time for the second application. The formula of critical clearing time remains the same. Only the formula of critical clearing angle is changing for both the applications. This is the concepts of equal area criteria. Now let us move on to the problem. Actually, okay, now if you see what actually they had given in the problem is a 60 Hz synchronous generator. Frequency is 60 Hz. Having an inertia constant H is equal to 5 megajoule per megavolt ampere. So the H they had given, inertia constant H, we had discussed in the swing equation derivation, which is the ratio of kinetic energy to the base power. This is the formula of H we had discussed in the swing equation derivation. Then had a direct axis transient reactance XD dash. They had given direct axis transient reactance XD dash is equals to 0.3 per unit. That is, this direct axis transient reactance corresponds to the synchronous generator transient reactance. SG, synchronous generator reactance. So here you had a synchronous generator, corresponding transient reactance is 0.3 per unit. And then what they had said is connected to a infinite bus. This is the infinite bus bar. Here it is the infinite bus bar through a purely inductive circuit shown in the figure. This is the figure they had given in the question. Reactances are marked on a common base system. All the reactances given are marked on a common base system. And then the generator is delivering a real power, PE. The generator is delivering a real power. PE is equals to 0.8 per unit. We know PE is equals to PM. So PM is equals to 0.8 per unit. And Q is equals to 0.074 per unit. To the infinite bus at a voltage of 1 per unit. The voltage at the infinite bus, V infinity, modulus of V infinity is 1 per unit they had given. So that only I had written. So this and all the given parameters, these are all given in the problem. Now what they had asked? They had asked first, a temporary three-phase fault occurs at the sending end. Sending end, this is sending end and this is the receiving end. So here there is a temporary fault. Here there is a temporary fault in the first condition. First subdivision of the problem is application 1. That is, a three-phase temporary fault occurs at the sending end of the line. At this point, a fault is occurred. When the fault is cleared, the both lines intact. Now we should find the critical clearing angle and the critical fault clearing time. That is del C and TC we should find for the first application. And then the second subdivision is a three-phase fault occurs at the middle of the one of the transmission line. That is at this point. That is application 2. Middle of the transmission line. The fault is cleared and the fault line is isolated. We should find the critical clearing angle at this condition. So they had asked, they had given a diagram and they had asked to find critical clearing angle and time for both the applications. That is when the fault is at the sending end and when the fault is at the middle of one of the transmission line. So let us start the problem. First thing is PE is equals to P max sine del. What is P max? P max is E dash V by X12 sine del. This E dash we had already known. E dash can be written as V plus J X into I. This I will be constant. So this X will be variable. What is this X now? How to find this I? I is equals to, we know that complex power S is equals to V into I conjugate. So from this, I conjugate is equals to S by V. I is equals to V conjugate by S conjugate by V conjugate. Now they had given S. What they had given? S, normally S is equals to PE plus JE into Q. PE they had already given. What they had given? 0.8. And Q they had given as 0.74 per unit. So you can find PE plus JQ. So you can find S. You know the value of S. And V is the voltage at the infinite bus bar, 1 at an angle 0. You know the value of voltage. So by knowing the value of S and voltage, you can get the value of current. If you substitute there, and if you find what you will get, the value of current, current can be obtained. The current what you will get if you substitute is, that is what is S? S is, S conjugate is PE minus JQ, no? So 0.8 minus 0.8 is PE. 0.8 is PE, Q is 0.074, no? So 0.8 minus J 0.074 divided by V plus J0, that is 1. So the current is also same, that is 0.8 minus J 0.04 is the current. Now X1 is the total impedance, that is before fault. Before fault, whenever we are solving for before fault, we should take total impedance, that is 0.3 plus 0.2 plus parallel combination of these two. 0.3 plus 0.2 plus parallel combination of two impedances. That will give you the total impedance. So X1 is equals to total impedance, that is 0.3 plus 0.2 plus this is the parallel combination of the two transmission lines, which you will get as 0.65. If you solve this, you will get this as 0.65. Now you got X1, that is total impedance, that is this value. You know this, and this V is 1 voltage at an infinite bus bar, and you know the current. You substitute this current here. You substitute this current here, and you know this X total is equals to, what is X total? Now only we got 0.65. And we know this V is equals to 1. So you will get E dash. First we should find the value of I by using S and V. Then substitute the value of I in the E dash equation, get the value of E dash. Once you get the magnitude of E dash, get the value of P max. Actually, P max is only this. The sign del is not. P max formula is this one. You should substitute this P max in this equation to get the PE equation. The final equation what you had got here is 1.8 sine del. That is the first condition. Now, we know that PE is equals to 0.8. They had given PE, it is delivering a power of 0.8. So 0.8 is equals to 1.8 sine del. From this, you can find what is the value of del naught. If you keep this PE is equals to 0.8 here, you substitute here, then sine del is equals to 0.8 by 1.8. From that, you find the value of del, which is del naught. Now, del max formula is 180 minus del naught. This is the formula for del max. We are using this del max term in the critical clearance angle, no. So del max and the formula is 180 minus del naught. So you will get the value of del max. Substitute the value of del max. You know the value of del max. You know the value of del naught. You know what is the value of PM. PM is actually 0.8. And you know the max. What is the value of P max? P max is this 1.8. So you will be getting the cos del C. One important thing is you should get this cos del C in terms of radians. Why? Because here you had pi, which is radians. Substitute the del C here to get the critical clearance time. This is the first application. Coming on to the second application. In the second application, the fault is at the middle point. At this point, we had a fault at this middle of the transmission line. So when the fault is at this point, what will happen? We should draw the corresponding equivalent circuit. This is the equivalent circuit. Actually, before it is like this. Like this, 0.3. Now, since the fault is at the middle, what I am doing, I am breaking the 0.3 into 0.15 and 0.15 and I am grounding the middle point. So this is the equivalent circuit. Before it is parallel like this. Two lines are there, parallel lines. Like this it is there with 0.3. Now since the fault is in the middle of that line, I break that into two equal halves, 0.15 and 0.15, and I am equating the midpoint to ground. So this is the equivalent circuit. Now what you should do, you should convert this delta, this star to delta, this part. As I had explained you in the derivation of power angle equation, we are converting the star to delta there also, right? The same thing we should do. We need to convert. This 0.5 is the combination of the generator direct axis transient reactance and the transformer reactance. That is, it is a combination of these two reactances. 0.3 plus 0.2 is 0.5. And since there is a fault, I am breaking this into two equal 0.15 and 0.15. I am connecting 0.15 to the ground. Now, here you had a star like this. Here we had a 0.5. And then here you have 0.15. And here you have 0.3. Now you need to convert this star into delta. And where will be this 0.5 lying? This 0.5 will be here. Here you have 0.15. We are bothering about this. So if you convert this star into corresponding delta, it will be coming like this. See, this is the delta. And the other end is here. This 0.15 is parallel. Here we are having that 0.15. So if you convert, what you will get, we will be getting 1.8 as upper end. This is 1.8. And here this is 0.9. And here you have 0.54. This is 0.54. Actually, before we had a star like this. This star we had corrected. This is 0.5. This is 0.5. This on this side of the star is 0.3. And this value of the star is 0.15. So I am converting this star. I had converted the star into corresponding delta. So I got upper side 1.8, here 0.9, 0.54, and the parallel one is 0.15. Now what we should take? This point is grounded. This point is grounded, so I can split this separately. So I had separated 0.9 as a separate branch and then 0.5 as a separate branch. Now if you see, as I had explained you, when there is a fault in the middle, for application 1, if you had seen the waveform, there is only one waveform for the application 1. See here, for application 1, we had discussed only one waveform. But when we are coming to application 2, we should discuss what is happening before the fault, after the fault, and during the fault. So for application 1, we had seen the generalized procedure. And coming on to application 2, we should see what is the before fault, after fault, and during fault. Coming to before fault, that is PE1 is equals to Pmax1 sine del 1. Here, that is, we had already calculated the value of this before fault for the first application, which is the same thing here also. PE is equals to 1.8 sine del. When we are calculating before fault, this Pmax will be having the denominator. No. What is Pmax? Pmax is E dash then modulus of V divided by x12. This modulus of V is the voltage at the infinite bus bar, which is 1 they had given. This E dash is V plus Jx into I. So we know the value of V, we know the value of X. X is the total impedance. And the value of I we had calculated by using S conjugate by V conjugate, and we had found out. And this denominator x2 dash, x12 is the total impedance for before fault condition. When we are solving during fault condition, this E will be same. E will be same for before, after, and during. So this is same. And this V is also 1 for all the condition. Only this x12 changes for before, after, and during. When we are calculating for during condition, PE2 is equals to P2 max sine del 2, where this P2 max is equals to E dash V by x12. E dash is constant. That is, we are calculating in the first case, V plus Jx into I. I is equals to S conjugate by V conjugate. Only x12 changes. When we are calculating for during condition, x12 will be is equals to 0.18. That is this impedance, this one. That is, in the delta connection, after converting the star to delta, whatever the impedance here we got, that is x12 for during condition. For before condition, x12 is the total impedance. For during condition, this is x12. Now let us move on to after condition. After fault happens, what will happen? this complete line after fault, this complete line will be isolated. No, this complete line will be isolated. So this complete line isolated, now this line is removed. So we had 0.3, 0.2, 0.3. So remove this line completely and take the remaining impedance as the X12 after fault condition. 0.3 plus 0.2 plus 0.3. That is for after fault condition. 0.3, 0.2 and 0.3. So 0.8 you will get. So you will be finding again PE3 for this. PE3 is equals to, for after fault condition, P3 max, P3 max sin del 3. This P3 max, how we will find sin del 3? This P3 max can be found out by using modulus of E or E dash, anything is same. That is sending a generator terminal voltage, and the modulus of V divided by modulus of X12. This X12 for the after fault condition is, you should remove this complete line. So this is the, you will be getting 0.8, corresponding value you will be finding. Then now you got all the things. Now del max is equals to 180 minus, in the previous case for application 1, how we found out the del max? Del max is equals to 180 minus del naught. This is formula for application 1. For application 1 and application 2, you should know what is the del naught, what is cos del C. Once you got the value of del C from cos del C, you can substitute in this TC formula. This TC formula remains same for all the application. For application 1, that is fault at the sending end, this del max is equals to 180 minus del naught. And coming on to application 2, the del max formula is, del max is equals to 180 minus X12 after condition and P by P max after condition. This is for application 2. This is for application 2. Now we had found out del max and we know the del naught. We know del naught, we know del max, we know P2 max, P1 max and P3 max. So using this critical clearance angle formula, this is the formula for application to critical clearing angle. Find the value of del C. As I had already said, P3 max is after and P2 max is during. And from this del C, you can substitute this del C in TC formula to get the critical clearance time for the second application. So with this, I will stop recording. This lecture is ended. Thank you.